Steam turbines is a mechanical device that converts thermal energy into mechanical power or rotary motion. The working fluid for steam turbines is water or water vapor. Okay, so similar to hydraulic turbine, it's use water, but now in the form of vapor. Okay, so steam turbine working on Rankine cycle that you have already learned in thermodynamics 2 consists of condenser, pump, boiler, and turbine. And this is the TS diagram for a Rankine cycle. And we look a little bit into each process in this cycle, which from point 1 to point 2 is an isentropic compression in pump, and 2 to 3, point 2 to point 3 is constant pressure heat addition in boiler, and 3 to 4 is isentropic expansion in a turbine, and 4 to 1 is constant pressure heat rejection in a condenser. We can calculate the work done by pump using the enthalpy value at 2 and 1, and the Q in or the heat addition inside the system using enthalpy at 3 and 2, and the work done by the turbine, and also the heat rejection by the condenser. And we can calculate the net work using the Q in minus Q out, or work done by turbine minus work done by pump, and the efficiency of this cycle using this equation. So all of this you have learned in detail in thermodynamics 2. So now we want to look into the principal operation of a steam turbine. Steam at high pressure and temperatures expands through nozzles, forming a very high velocity jet. So in steam turbine, we use convergent divergent nozzle to direct steam onto a turbine blade. Okay, so this is the inlet of the nozzle, and this is the outlet of the nozzle where the steam will be directed to blade of the turbine. Okay, you can see here the shape of the nozzle is first convergent here, and then divergent in the next section. Okay, so it have first section convergent section, and the second section of the nozzle is divergent nozzle. So this kind of nozzle is called convergent divergent nozzle. And then this is from the nozzle, steam will go to the stationary blade. So the left side of this this figure, stationary blade, and then the stationary blade will guide steam into the blade of the turbine. Okay, so this is the stationary blade or the stator, and this is the rotor or the blade of the turbine. Okay, we have two kind of blade. One is stationary blade or stator, and one is the rotary blade or rotor. Okay. So in steam turbine, the convergent divergent nozzle, we use a series or a few such nozzle mounted on the inner wall of the cylinder of stator casing. Okay, and then the rotor of the turbine have blades fitted around a circular array, as you can see you can find the images in Google or in the video that I have provided last night. Okay, so you can see the turbine is circular and there are many nozzles fitted on the casing of the turbine, and steam jet from static nozzle. Okay, so for example, this is where the nozzle, and the steam will go from the nozzle to the stator and glide into the rotor blades. Okay, so when steam hit the rotor blade, it will cause the blade to move. Okay, or to rotate. Okay, a set of stationary blade and rotor blade is called a stage. Okay, so a set of stator and rotor is called a stage. And then the design of the blade or the number of rows of static and rotating blades produce the requisite torque. It produces the power to move or the torque to rotate the turbine. And type of turbine are classified according to the arrangement and shape of these blades, especially the rotor blade. Okay, so based on the nature of blade profile, steam perform work on the blades differently. And there are two types of turbine, as we have learned before this, which is the impulse turbine and reaction turbine. And steam turbine also classified into these two types. Okay? The impulse steam turbine and reaction steam turbine. Okay, now we want to look into the simple impulse turbine. This is the construction of a simple impulse turbine, which consists of a converging, diverging nozzle here, converging and diverging nozzle, and then this is the blade or the rotor. Okay, the blade or the rotor. Okay, so the steam will enter the nozzle and exit the nozzle into the rotor. Okay, if we look below this is the pressure and velocity diagram of a simple impulse turbine. As we can see here, when steam enter the nozzle, inside the nozzle, the steam pressure will drop. Steam pressure will drop while the velocity of the steam will increase inside the nozzle. And then steam will enter the blade at a very high velocity. Okay, steam will enter the blade at a very high velocity. Some of impulse turbine can go up to 1,100 meter per second, which is in supersonic velocity. Okay, and then inside the blade, the pressure remain constant. The pressure of the steam remain constant while the velocity of the steam is reduced inside the blade due to some of the energy is already absorbed by the blade to move the rotor. Okay. Even though the exit velocity is reduced, but it's still in a considerably high velocity. Okay. And this high velocity at the exit of the blade will cause some losses to the kinetic energy, which is about 11% of the initial kinetic energy value. And this high velocity at the exit of the blade will cause a very high rotational speed. In result, the turbine will require a large gearing arrangement to drive the generator. Okay. So it is undesirable to have a very high rotational speed. So this is what happened inside a simple impulse turbine, a simple steam impulse turbine. Okay. So what we have to do uh, to solve this problem of high RPM or high rotational speed is to use compounding stage, okay, or compounding of impulse turbine. This is a method of reducing rotational speed of the simple impulse turbine to a practical limit. And this is also reduces the exit at the exit loss, the loss at the blade exit. And the compounding is done by making use of more than one set of nozzles and blades in series, so that either the steam pressure or the jet velocity is absorbed by the turbine in stages. Okay, there are three types of compounding. Okay, the first one is pressure compounding. The second one is velocity compounding. And the third one is the combination of pressure and velocity compounding. We will look into the pressure compounding first, or it's also called ratio stages. In pressure compounding, if you look into this diagram, here we have this is the nozzle. Steam go through the first nozzle and then into the first blade. Okay, if it's just a simple impulse turbine, it will only have this part to rotate the generator. But in pressure compounding, we have several of this stage. Okay, so we have, this is nozzle number 1 and blade number 1. And then here we have nozzle number 2 and blade number 2, and nozzle number 3 and blade number 3. So this is one stage, and then this is another stage, or the second stage, and this is the third stage. So pressure compounding have few stages of nozzle and blade or stage. Okay, so what happened in this kind of arrangement, you can see here the pressure and velocity of the steam. Okay, pressure of the steam will reduce in nozzle, while the velocity will increase. And inside the blade, the pressure remain constant. Okay. Inside the blade, the pressure remains constant while the velocity is reduced. And then this process happens for a few cycles, depend on how many stages it have in the turbine. So in the end, the pressure will come out at a condenser pressure value, and this from high pressure to low pressure happen in stages. Okay, it's not drastically reduced, but it reduced in stages. Okay. This results splitting up the whole pressure drop from the steam chest pressure to the condenser pressure into a series of smaller pressure drops across the several stages. And we know that pressure reduces only in the nozzles, while it remains constant in the moving blades. Since pressure drop in each nozzle is reduced, steam velocity and hence the blade velocity is also reduced. And this will also reduce the kinetic energy loss to 1 to 2% of initial value. So before this, we know that in simple impulse turbine, the kinetic energy loss is about 11%, but by having these reduced stages, the kinetic energy loss is only 1 to 2%. Okay, so pressure compounding is just simply a few set of stage. Okay, a few set of stage. We know that a stage consists of a nozzle and blades. Okay, so a nozzle and blade is one stage, and then in pressure compounding, we use several stage of this nozzle and blade. Okay. And next we look into velocity compounding. The velocity compounding, unlike pressure compounding, it only consists of a set of nozzles and many rows of moving blades attached to rotor and many rows of fixed blades attached to casing which arrange alternatively. So in velocity compounding, we only have one nozzle or one set of nozzles. Okay. In pressure compounding, we have many sets of nozzles. In velocity compounding, we only have one set of nozzles at the entrance, and then many sets of moving blades and stationary blades. Okay, many sets of moving blades and stationary blades. So the stage or the stages in velocity compounding consists of stator and rotor, or guide blade and rotor blade. So there are many set of guide blade and rotor blade, but only one nozzle. So what happened in velocity compounding, or also called Curtis stages, and we know that in the nozzle pressure will drop and velocity will increase, velocity of the steam and pressure of the steam. Okay, and then in the blade, we can see here across the blade or across the stages, the pressure remain constant. Okay, while the velocity of the steam is decreased gradually or decreased in stages. Okay, so that's why this is called velocity compounding, where the velocity is decreased in stages. Pressure compounding, the pressure is decreased in stages, but velocity compounding, the velocity is decreased in stages. Okay, the whole expansion of steam from steam chest pressure to condenser pressure takes place in nozzles only. No pressure drop takes place either in moving or fixed blades. Steam velocity drops gradually at every stage of moving blades. There is only a negligible velocity drop in fixed blades due to friction. Okay, because fixed blades that does not absorb any energy from steam. Okay, but some losses is only due to a minor loss of friction. So this is velocity compounding. So we have learned here the classification of impulse, the classification of steam turbine, and the pressure compounding and velocity compounding of steam turbine. Okay, so as the name implies, pressure velocity compounding have both effect. Okay, the pressure staging and the velocity staging. So if you look into this diagram, okay, first we have nozzle, all right, and then we have moving blade, okay, moving blade here, and then this guide blade or stator, and then another moving blade. So inside nozzle, there will be pressure drop, okay, and then inside the blades, the moving and the guide blade, pressure will be constant, while the velocity is increased inside the nozzle and then decrease inside moving blade, constant in guide blade, almost constant, and decrease again in moving blade. So this is the first stage of the velocity compounding and pressure velocity compounding. So we have, so this is one stage, and we have another same stage here, which is we have another nozzle and moving blade, guide blade, and moving blade again. So exactly similar component of the first stage. At the second stage, we have nozzle, moving blade, guide blade, and moving blade. So again, the pressure will decrease in the nozzle and then remain constant at the condenser pressure. Okay, so the pressure is decreased in two stages here. Okay, while the velocity will have another stages of decreasing velocity inside the turbine, inside the moving blade, inside the second stage. Okay, so this is a combination of pressure and velocity compounding. There are two sets of nozzles where the whole pressure drop takes place. Okay, nozzle in the first stage and nozzle in the second stage. Set of nozzles and set of nozzles. After each set of nozzles, there are more than one moving and fixed blade rows arranged alternatively. So in this example, we have only two moving blades, two rows of moving blade and one row of guide blades in one stage. But we can have as many stages as possible, depend on the design of the whole turbine. Okay. So hence velocity drop also takes place in steps. Okay, so in pressure velocity compounding, the pressure drop takes place in stages, as well as the velocity drops also takes place in stages. We have also another type of steam turbine, which is impulse reaction steam turbine. Okay, now we just talk about impulse steam turbine, but we will look into reaction steam turbine as well. And then we will do a comparison between impulse turbine and reaction steam turbine. But before we do that, we will do that in next week. But before we do that, I want you to look into how we analyze the velocity triangle inside steam turbine by looking at the video that I have attached in Google Classroom. All right. So there are velocity triangles and also efficiency of steam turbine in that video.